Imagine harnessing the power of a star, right here on Earth. A single teaspoon of fusion fuel could generate more energy than millions of gallons of gasoline. Welcome to the world of nuclear fusion, where scientists are racing to unlock the universe's most powerful energy source. Tonight, we'll explore every facet of this quest, from plasma physics and reactor designs to the global fusion race and its potential to transform our civilization. Get ready for an illuminating journey into the future. Fusion is the process that powers the stars. At millions of degrees, hydrogen nuclei fuse into helium, releasing energy as described by Einstein's E equals mc squared. The challenge is, how do we recreate this in a controlled environment on Earth? Today, we have two promising approaches: magnetic confinement using tokamaks and stellarators, and inertial confinement using high-powered lasers. Let's start with magnetic confinement. In a tokamak, hydrogen isotopes, deuterium and tritium, are heated into plasma at temperatures exceeding 150 million degrees Celsius, hotter than the core of the Sun. Powerful magnetic fields, generated by superconducting coils, hold the plasma in a donut-shaped vacuum, preventing it from touching the reactor walls. ITER in southern France is the world's largest tokamak under construction. When fully operational, ITER will produce 500 megawatts of fusion power from only 50 megawatts of input, a tenfold energy gain, the critical milestone known as Q equals 10. But this epic ambition comes with soaring technical challenges. Building superconducting magnets that stay cold at minus 269 degrees Celsius while conducting megaamps of current, managing powerful neutron flux that degrades materials, and sustaining stable plasma for minutes or longer. Another approach is the stellarator, a twisted three-dimensional cousin of the tokamak. Stellarators, like Germany's Wendelstein 7X, use precisely shaped magnetic coils to trap plasma without the need for huge currents inside the plasma itself. This eliminates many of the tokamak's stability issues, but folding and building those complex coils is a monumental engineering feat. Meanwhile, on the other end of the spectrum lies inertial confinement fusion. Here, a small pellet of hydrogen fuel is zapped at once with ultra-powerful lasers or particle beams, compressing it rapidly to trigger fusion reactions before it can expand and cool. In 2022, the U.S. National Ignition Facility made headlines by achieving ignition, producing more energy from fusion than was delivered by the lasers to the fuel pellet, a landmark moment. But converting that into continuous affordable power requires breakthroughs: faster repetition rates, tougher optics, and more efficient thermal extraction. Whether tokamak, stellarator, or laser fusion, one common challenge is plasma physics, understanding turbulence, instabilities, and heat loss at extreme temperatures. Today's computational models, powered by supercomputers, simulate plasma behavior in 3 dimensions, helping designers improve reactor shapes and magnetic configurations. Artificial intelligence is also stepping in, optimizing plasma control systems to maintain perfect confinement in real time. Let's zoom in on 2 flagship projects. ITER, an international collaboration between Europe, the United States, China, Russia, India, Japan, and South Korea, began construction in 2015. 8 years later, over 90% of components have been delivered: toroidal field coils, cryostat walls, superconducting magnets. First plasma is expected by 2025, and deuterium-tritium fusion experiments by 2035. China is building its own path. The China Fusion Engineering Test Reactor and the Super Ring Stellarator, the so-called shooting star, are prototypes to elevate China's leadership. The artificial sun research at Hefei Institute pushes plasma parameters to record levels, showing China's serious ambitions. But fusion is more than just science. It's an economic and political race. The promise of abundant, clean, baseload energy, free from greenhouse gas emissions, radioactive waste, or weaponization, has policymakers' attention. Fusion startups like Commonwealth Fusion Systems, TAE Technologies, and Helion Energy are racing to build compact modular reactors that could power grids by the 2030s. Heat-treated blanket materials like silicon carbide composites, lithium lead eutectics, and tungsten walls are being tested to survive neutron bombardment and convert heat to electricity. Fusion's environmental promise is staggering. A single gram of deuterium-tritium fuel can release as much energy as burning 8 tons of fossil fuel. With deuterium abundant in seawater and tritium bred inside the reactor's own lithium blankets, fuel scarcity isn't a concern. Fusion reactors produce virtually no greenhouse gases and generate minimal radioactive waste, short-lived, low-level fission products rather than long-living transuranics. This could be the clean energy revolution that finally frees humanity from carbon constraints. Yet fusion is not a magic bullet. Economics matter, capital costs are enormous, and building a fusion power plant demands a complex supply chain, regulatory support, and public acceptance. Governments, private investors, and international bodies must coordinate for decades. So, what will the future hold? Will ITER demonstrate sustained burning plasma in time? Will compact reactors be ready by 2035? Can fusion unlock limitless energy and lift billions out of poverty while reversing climate change? Or will it remain a scientific marvel whose benefits arrive too late? One thing is clear. We stand at a pivotal threshold. Fusion is humanity's final frontier in energy, where science meets destiny, innovation meets policy, and ambition meets perseverance. The dream of harvesting a star's power has never been closer. If we choose wisely, fusion could redefine civilization. If we delay, the world pays the price. Stay with Synaptech for ongoing updates on ITER, fusion startups, laser ignition breakthroughs, and cosmic technologies. If this deep dive sparked your curiosity, press like, subscribe, and hit the bell icon. Together, we'll watch as humanity reaches for fusion, lighting the way to a brighter tomorrow.